What up, dudes? Let's get this party started on Archives. Please excuse the 3D printer. It's going and it's making a bunch of sound. But anyway, let me kind of recap for you what logarithms are, what the properties are. Hopefully, we'll have some time to really just get into it today. All right. So check us out. We talked about inverse functions in the past, and inverse functions were like, if I have y equals x squared, y equals x squared, what we're doing is, what is the inverse of y equals x squared? Well, we talked about how if I draw a dotted line right over here, and I did that thing where I folded the paper and all that kind of stuff, then I would get what we call the inverse, and the inverse looks like this. And we're actually quite familiar with that graph. That is, as Lucas is suggesting, the square root of x. You're absolutely right. But it's actually plus or minus the square root of x, mainly because this is the plus part and here's the minus part. We cool? Now technically this inverse function is not really a function, because I told you, in order for it to be a function, it has to pass what we call the vertical line test. In this case, see this graph right here? That doesn't pass the vertical line test. If I draw a vertical line, it only needs to, it can only pass 1 point. But that's why I have two separate functions graphed up here at the same time, and I have the plus or minus x over there. All right, to find the inverse function, here's what you do. You have the y equals x squared, and then we want to invert it. So what I'm going to do is I'm going to switch the x and y components. Or, yeah, exactly, x equals y squared. And then in order to find that thing, what we need to do is solve for x exactly. So then I say the square root of x equals y, but when I take the square root of both sides, I better add in a plus or minus sign. And hence, the y is equal to the plus or minus the square root of x, and that's how we got it. Are we cool? Now, one of the things, and Diamond, you've seen all of this stuff before, so bear with me. I'm just kind of recapping all of the stuff we did on Friday, or on Monday, or Wednesday, whenever we talked last. But one of the things that is a really big advantage is, or here, I'll tell you a problem. We had a problem that involved exponentials, okay? So this is a separate piece right here. On the right side of the board, I'm going to do something different. We had a problem that involved exponentials, and it was something like you invest a certain amount of money at a certain rate for certain years, and you guys know what that we know what the graph kind of looks like. That is what we call exponential growth. Are we cool with that? Something like that, right? So that's the graph of like some kind of investing some kind of principal, like $1,000 at a rate of 3%, and you compound it every month, so n is 12, and this is expressing for t years, so this is what the graph looks like. And you've guys gotten really good at these exponentials, right? But then I would always ask a question, or every so often I would ask you a question like this. If you invest $1,000, how long would you have to wait in order for your investment to double? Okay? How long would you have to wait in order for you to double the amount of money you made? And how did you guys do that? I'm just curious. In the past, or like before you learned anything about it. Okay, well here's what I suggested to you. Trial and error, okay, maybe that might work. Here's what I suggested to you. I said, hey, if you go down to Desmos and you graph it, okay? So like this right here is your original investment, right? But if you go into Desmos and you graph it, you can look on Desmos and you can say, well, double the investment is about here, okay? And then what I would do is I'm going to give you, I guess the question I'm asking is, I gave you the output. What is the input? Because normally this graph, the way you use this graph is you say, all right, you wait a certain amount of time, so time is your input, and then the output is how much money is your investment worth, right? So there's your input and output. But this time I'm asking you the question a little bit backwards. This time I'm saying, well, here's how much money I want. How much time did I have to wait in the beginning in order for that to happen? So I gave you the output and I'm asking for the input. And the only way that you guys knew how to do that is to graph it. And then you say, okay, on Desmos, I'm graphing this. And then when you zoom in over here, you can see the Y value. And then you look down over here, and then you can see the corresponding X value that gives you that amount of time. And I would ask that question like, you have a group of leopards and they triple every year, and how long will it take for them to reach a population of 3,000 or something like that? Are we cool? But here's the thing. Here's the thing. If I took the inverse of this, so if I inverted this, or took the inverse of this, that graph would look like this, right? So this right here is y equals a to the x power. And this right here is the inverse of that, where I have it switched. No, it's a to the x power, not x to the a power. Okay. And this is the inverse of this. Then, well, actually here, I'm actually explaining to you why the inverse is important. Check this out. The input of this is going to be the output of this. Here. Let me kind of explain it a little bit better to you. Let's go back to those parabolas that we're doing. When I want to graph a parabola, okay, and I make a table for a parabola, then I can go like this. If I put in 1, what comes out? 1. If I put in 2, 4 comes out. If I put in 3, 9 comes out. If I put in 4, 16 comes out. Okay? This is for y equals x squared. So your y is equal to whatever you input squared. Does that make sense to you? We're kind of jumping back and forth between these two parabolas. So what if I were to make another table for you, and I did this one? Y equals the square root of x. Okay, so if I input, and I'm writing it a little bit different here because usually I'm writing the words x and y. But in this case, I'm actually writing in and out. It's the same kind of idea here. But check this out. The input over here, if I input 1, what is the square root of 1? It's 1. If I input 4, what's the square root of 4? 2. Good. If I input 9, what's the square root of, that's 3, and then 16 is 4. Are we cool with that? Now look at this. The input over here is actually the output over here. And the output over here is the input over here. Yeah. Basically, the x and y's got reversed. They got switched. You can see it clearly on the table, right? And we know that these are inverted functions. This is the inverse of that function right there. So if I were to ask you something like, if I were to say, so like over here, you would have this graph, and then if I were to take a look at just a parabola, okay? And if I were to ask you something like, if the output of my parabola gave me 25, then the input must have been what? And don't answer it yet, don't answer. I know that you guys already know the answer, but if I said something like, if the output of my y equals x squared was 25, what must have been the input? Okay? Then what you guys could do, is you can say, well, if you have an output of 25, but I know the inverse function, then if I put an input of 25 in the inverse function, the output is what? You take the square root of it, and then what is that? It's 5. So, check this out. If I gave you an output and asked you for an input on the original function, what you guys could do is you guys can turn to the inverse function and then give it that input that I was originally asking as the output over here, and then figure out what the output is over here, and that's what the input of that function would be. Did I confuse you more, or did that make sense? Okay, so that would really help us with this exponential problem, right? And you could see exactly how this exponential problem could be very relevant to your lives, right? You can see how that could work. Because what we have is, I ask a question like, I give you the output, what is the input? And the only way you've learned how to do that is to graph it. And that's not the exact answer, that's just an approximation that says, it looks like it could be around here. But it's not the way we could analytically do things. What we could do is we could find the inverse graph, and then from that inverse graph, we would take whatever output you gave us and make that the input here, and then whatever the output here is the answer to the input for here. Does that make sense? Boom, nice. Okay, so this right here, that's what a logarithm is. Logarithms are just the inverses of exponentials. They're not magic, they're not crazy, but they have these really cool, really useful, really incredible properties that I need to show you. It will blow your mind. Like when you have the inverse of these things, you'll realize that actually multiplication and exponential, you can do stuff that a calculator could only dream of doing. In fact, the only way your calculator and your computer know how to do certain things is because we knew the mathematics of logarithms. The only way it can calculate really big numbers and crazy big numbers is because of logarithms. Yes. So, why is this relevant to your lives? Well, because it was relevant to mathematics. And that could be relevant to your life. All right. Let me show you something real quick. Can I erase this part? This is exactly what we went over on Wednesday. All we did on Wednesday was we talked about this inverse relationship, and I did the quick version over here. And I think I even did a better job this time. All right, so check this out. If I have some exponential, like for example, let's make it a to the b equals c. Now these are just straight up, these are different numbers and all of that kind of stuff. But maybe I should do it like this. A to the x equals y. All right. If I want to find the inverse of this, what do? I switch the x and y's, right? So it's a to the y is equal to x. And I solve for y. Right? I just take the x over here and I just switch them around. And then I solve for y. The problem is there is no way to solve for y. It doesn't make any sense at all. Like, how do you get y all by itself? Y is in the exponent. I can't divide by anything. No. So what we did was we came up with this new way of writing things. We said, all right, fine. If I have the log base A of x, that's equal to y. And it's a notation. So now look, I've solved for y. I got y all by itself. Y is equal to the log base A of x. You know why it's the base A? Because I'm all about it. I'm all about that one. This one, this right here. The base. I'm about the base. About the base. No treble, but about the base. Yeah. All right. Anyway. So, check this out. This is the equation I want you to write down. I want you to write it down. I want you to be familiar with it. If you're taking a test, maybe you might have to memorize it. But, you know, I mean, maybe you don't have time to. I don't know. We'll see. You'll usually see it like this. Log base A of C is equal to B translates to A to the B equals C. And I kind of look at it like this. I kind of look at this log like a scorpion. Let me show you real quick. Hey, what's going on, Kai? Teaching about logs, but you're downstairs doing all kinds of crazy stuff. All right, here, let me show you. So I want you to memorize this one right here, or write it down. This is the same thing. They mean the same thing. They're just two ways of looking at the same exact thing. If I write down this, you could write down this, and it's the same. Got it? All right. So here's what we got. When I write it down, log base A of C equals B. I kind of think of this like a scorpion. You know, like a scorpion's tail. And a scorpion kind of looks like this. It's got a body over here. It's got some pinchers over here, and it's got a tail that kind of comes around like this. Cool. So you start at A, you work your way around, and you hit B. And then you come around here. All right, so you start at A, you work your way around, and you go up to B. And then you cross the equal sign, and that's equal to C, because it points to C. So on the journey of the scorpion's tail, that's kind of how that works. That's how I memorize it. I know. I don't know if that's really easy for you to do or not, but that's what I saw. Okay? So, let me give you an easy problem to begin with. I'm going to give you an easy thing to kind of solve. 2 to the x is equal to 8. Think about it. 2 to the x is equal to 8. What is x? Okay. I see where you're going with that. But Lucas, really think about it. What does x have to be in order for this answer to be correct? 2 to what power equals 8? How many times do you have to multiply 2 by itself in order to get 8? There we go, Sophia. Exactly, it's 3. Right, 3 times. 2 times 2 times 2 is 8. Does that make sense? So check this out. We didn't need to use logarithms in this case. Right? We didn't use logarithms at all. We were just able to look at it and say, oh, it's 3. Got it? But what if I did this? What if I did this? What if I said 2 to the x power equals 10. Then 2 times itself, how many times equals 10? Well, that you don't know. But like what you guys said, I agree with you. We could write that as log base 2 of 10 equals 2x. Are we cool? So then here's kind of what I'm getting at here, okay? Usually we see this, okay? Usually we see this. 2 to the x power equals y. And then I ask you something like, if x were 5, then what is y equal to? And then you would plug in a 5 for x, and you would get out your y. Are we cool? But now what we're doing is I'm saying, well, let me give you the y, and I want you to tell me what the x is in the first place. So then I say, the y is equal to 10. Now, back when that was 8, that was easy to do. Because 2 cubed is 8. It's a nice number. It's a pretty number. I mean, if the next number were, if this were 16 instead, it would be easy, and I wouldn't need logs at all. I can just say, oh, it's 4. 2 times 2 times 2 times 2 is 16. We're good. But for this one, this is where logs come in. Now, I want you guys to open up Wolfram Alpha. Okay? And I want you to write this. Log underscore 2 parentheses 10. I think that's Wolfram Alpha's way of writing log base 2 is equal to 10. Or log base 2 of 10. And then have it calculated out for you. What is your answer? I'll tell you what I'm going to guess the answer to be. Someone said 3 point something, and I agree with them. Because if this were 8, then x is 3. If this were 16, then x is 4. So I'm guessing that x is going to be somewhere in between 3 and 4. In fact, I would even venture to say it's closer to 3 than it is to 4. Now, Lucas got 3.32. Sure, all right, fine, Lucas. X is equal to 3.32. All right, cool. That's how you use logs. Now, the base of a log is actually a way that you're counting. It's a way of counting, okay? So if I have a log base 2, that would almost be like I'm counting by pairs. I'm counting of pairs of things. Does that make sense? Now, strictly because, and I kid you not, okay, let me write the equation up there again. Hold on. A to the B equals C translates to log base A. There. All right. I kid you not that this is actually, I really think this is the reason. One of the most, you know how like when we write square roots or cube roots or fourth roots, if we write a cube root, we put a cube root like that. If we write a fourth root, we do this. But if we write a square root, we just do this. There should be a 2 there, but we're so darn lazy that we just like, screw it. 2 is supposed to be there, just assume. If nothing's there, assume a 2. We cool? Well, the same kind of goes for logs. If I write just this, log of, I don't know, some number like C, then you automatically assume that it's a base of 10. I didn't write it there. I don't need to write it there because we're that lazy. We just kind of write no 10 over there. On your calculator, there's a log button. It's right over here. Got it? And the log button is assuming that A is equal to 10. The base is 10. Because it's the most common grouping of stuff to count by. How come? Because we have 10 fingers. Like that's really how it is. Humans have 10 fingers. If humans had 8 fingers, I'm sure that the most natural log that we can think of is log base 8. I'm sure that that's the way we would operate. If humans had 16 fingers, we would think of things in hexadecimal, and then we would basically have log base 16 as our most commonly used log. So if you have log base 10, you just write log, and that's the most popular one. All right. Also, look at this. You know, on a calculator, when you press if I press the second button, it's hard to see because it's all mirrored. But if I press the second button, then look at sine. I'm going to get the inverse of sine or cosine. When I press the second button, I press the inverse. I get the inverse of cosine. What happens when I press the second button and the log button? Look at this. I get an exponential function with 10 to the whatever. Right, because those are inverses of each other. So you have logs on one side, but when you press the second button, you get 10 to the x power. Does that make sense? Do you see how they're related to each other? All right. There's one more log I need to teach you about. And in your calculators, let's see, I don't ever remember what this number is. Okay, I taught you about this number E, and it's equal to 2.71828. 2.71828. We've used this before. You've seen this before. Is y is equal to e to the x power. This is a very natural number in science that occurs when you have growth of bacteria, right? It's continuous growth, and it's just a number. It's like pi, but it's a different number than pi. It's e. Are we cool with that? When you have log base e, so we can make this number on the bottom here, the base of the number, any number we want. But when I have log base e, there's a very special, it's almost like the world kind of made sense. And so what we call it is the natural log. It's the log of nature, which is not made of wood, apparently. And we abbreviate that LN. Look over here. The log button is right there. Below that is LN. That's the natural log. That's basically just log base E. But look, also look very closely. If you press the second button, what do you get? E to the x. Exactly. You undid the log, and so basically you're getting E back. Does that make sense? So that's how those two are related. All right. Here's some properties of logs. I'm going to write them down. We can analyze them, but I want you to, we can analyze them. You ready? I'm going to erase this. You guys should have written it down, hopefully. All right. Properties of logs that I think are really cool. Now, I'll be honest with you, I don't have time. So I'm going to do my cardinal sin and just pull equations out of, and throw it up on the board and say, look at these, memorize these. Maybe not memorize them, but at least write them down. Maybe you should memorize them. All right, you ready? Log base A of 1 is equal to 0. That is a rule. All right, what about this one? Log base A of A is equal to 1. Log base A of A to the x power is equal to x. There's some more of these things that are super helpful, but apparently this thing's not giving you anything to help you out with it. So, or this thing's not teaching you any more than I wanted to teach you. All right, fine. Let me prove them to you. I'll tell you what. I hate that. I hate the idea of just pulling equations and say memorize these. They're useful, and they are useful. But I mean, this makes sense to me. Check this out. If I were to write this in that rearranged form, this would be A to the 0 power is equal to 1. Right, A caret 0 is equal to 1. So it doesn't matter what A is, because if you're bringing it to the 0 power, it's equal to 1. All this is saying is that anything to the 0th power is equal to 1, and we already knew that. That's just the same rule written in log form. All right, let's do this one. Changing it to that thing, using that scorpion technique. So I go A to the 1 is equal to A. A to the first power is equal to A. Is that true? Yeah, there we go. Anything to the first power is equal to itself. That's what this is saying. This makes sense to you. If I were to write this on the board for you, you would have been like, no, duh, right? But when I wrote it like this, you're like, oh, wow, that's fascinating. I never knew. But it's the same thing. This literally is like duh, but you just haven't seen it in that form before. All right, what about this one? This is saying A to the x power is equal to A to the x power. No. Really? A to the x power is equal to A to the x power? Yeah. That's kind of pointless, isn't it? Actually, Sophia, this one right here is probably the most useful of them all. All right. Here. Let me show you how useful it is. What's 2 cubed? 8. Good. What is 2 to the 476th power? Okay, so the way you start this is you do a table. And you go like this. You go 2. Actually, here, we'll just start listing out the numbers. We can go 2, and we go 4, and then double that, so that's 8. And then the next one is 16, and then 32, and 64, and 128, and 256, right? And then we're going to do that 476 times. So 476 numbers later, I'll tell you the answer. Give me a second. Right. That's a little ridiculous. You can't do it. So here's what we're going to do. What I'm going to do is I'm going to take the log of both sides. To the 476 is equal to log of x. And I don't want to take the log. Well, maybe I can. All right, cool. So does that make sense to you? So I took the log of both sides. I still haven't figured out what my number is. But check this out. This can be dropped out in front. That's another property. Maybe I didn't highlight that property, but that's another one. You can take whatever's in this exponent right here and multiply it out in front. So it becomes 476 times the log of 2 is equal to log of x. Okay? So use your calculators. I'll use mine. What's the log of 2? It's 0.3. 0.3001. And I'm going to multiply that by 476. Are we cool with that? Times 476. So it's 143.29. Okay. So wait, let me just write this out here. Log base 10 of x is equal to 143.29. Cool, all I did was I wrote it. But this doesn't follow the formula we just learned. Oh, no. This is another property of logs. And you take this thing and you move it out in front. Anything to the exponent, you can move it out in front. This is the big advantage of logs. It's kind of based off of, I'll be honest with you, I shared with you 3 properties, but this is the only useful one. I hate to say that, right? Celeste, would that be a good, accurate description of logs? There's so many different properties of logs, like log base a of 1 is equal to 0, or log base a of a to the x power is equal to x, or something like that. But the only one that's really useful to me is if you take the log of something and you have the log of something to the exponent, you just take that exponent and you kick them out in front. That's the one that's like, so like what they're asking me is, I'm talking to another teacher, but what they're asking me, my students are asking me is, how do I know which property to use? And I would say, look, there's a bunch of different properties, but the only one that's really useful, there's only really one, right?
Unless you're simplifying.
Yeah. There's other ones that are useful, I guess, but this one's like the most useful by far, at least for scientists and mathematicians, I think. Because I think the rest of them the computer can take care of. You know what I mean? Anyway, let's rewrite this inside of our funky notation. You ready? So we do that scorpion kind of deal. So I have 10 to the 143.29 is equal to x. Are we cool? And then what I do is I do this. 10 to the 143 plus 0.29 is equal to x. This is going to make sense to you. I could write this as 10 to the 143 times, actually, you know what, I'm going to write it like this. I can write it like 10 to the 0.29 times 10 to the 143 equals to x. And I would venture to say that we already got our answer. This is our answer. You could figure out what 10 to the 0.29 is. 10 caret 0.29. And that answer is 1.94 times 10 to the 143 is equal to x. Have you seen this type of notation before? Maybe you've seen it in chemistry before. It's called scientific notation. Yeah, it should be important. Yeah, there we go. So I would venture to say that this number doesn't matter, though. The only number really that matters is this 143. And let me justify myself. Okay? The reason why it doesn't matter is because of this. If you had $1 billion, okay? And which would you rather me do? Would you rather me change it from $1 billion to $2 billion or multiply it by some number? Or would you rather me add zeros to your $1 billion? Right. I would rather add zeros. Right? Like, if you add 3 zeros, that's $1 trillion. That's 1,000 billion dollars. You see what I mean? So, like, the number in front, like the $1 billion or $2 billion or whatever, that pales in comparison. I mean, so say that you have two people who take those two paths, right? Like, let's say that Mr. Dalday says, well, I'd rather take the 2, multiply my number by 2. So over here, I'll have $2 billion. And then over here, Diamond's on this side, and she'll be like, dude, I've got $1 trillion, right? Like, I'm the schmuck who took that. So what I'm saying is, when you're getting into really large numbers, the number out in front doesn't really matter in comparison to how many zeros you have. Right? And we use this idea a lot when we're talking about science because we use we call this a Fermi approximation, or like we use this when we're talking about like the distance between stars. When we're talking about like the distance between stars, like if it were like 1 trillion or 2 trillion, that 1 or 2 doesn't matter. The fact that it's 9 zeros or 12 zeros or whatever, how many zeros, that's what's important. So it's almost like the zeros, the number of zeros, the place holder becomes more important than the actual number out in front. I would almost venture to say that even if this were a 1 out in front, or it's a 1.94, essentially it's the same number, right? Because they have 143 zeros. I mean, yes, technically, this is a bigger number than this. Technically, you're right. You're absolutely right. This is a bigger number than that. But pretend that this is dollars. You have 1.94 times 10 to the 43, $143. That is more money. That's like, okay, all right. Maybe not dollars, because I can't even imagine a world, like all the money in the world converted to pennies wouldn't equal close to that number. Maybe we'll do this. We'll go like this. If I have 1.94 times 10 to the 143, it takes that many grains of sand in the universe. Okay? So there's this many, let's pretend that there's this many grains of sand not in the universe, but in our galaxy. Let's say our galaxy. That sounds reasonable. So between Mercury and Uranus, no, Neptune, that's the last one. Sorry. Between Mercury and Neptune, there's this many grains of sand if I counted them all up together. So then, like, here's my question. If I add 3 more grains of sand to your number, is that really going to make a difference? No. Like, you would almost say it doesn't matter. Now, if you add enough sand to actually change this number, then I would say it matters. But if you add like 3 grains of sand and it's talking about that many zeros, I wouldn't even be able to tell you that I knew the difference. You know what I mean? So the only important number is this number, the 143. All right, now let me show you the point of what I'm trying to get at here. Check this out. Before we had a computer, now I got a question. In your calculators, can you do that? I wonder what my calculator would say if I put 2 carat 476. Okay, here's what I got. Now your calculators might be better than my calculator, and so it says overflow error. Yeah. It says, are you freaking kidding me? That's way too big. No, literally, that's what I pressed. I pressed 2 carat 146 or 476, and I got this. Imagine back in the day before there were calculators, when we didn't know how to do, when my calculator apparently isn't as good as Lucas's calculator. Imagine back in the day, before calculators, when we had to do some kind of number like this. Well, what we would do is we would use these logs and we would look up what is log of 2, and we'd have this little a book of all of these tables of answers, and one of those answers was what is the log of 2. And so we would look on our log table, and we would say, well, we know what the log of 2 is. And so then what we're going to do is, since we know what log of 2 is, then all we have to do is multiply 476 times 0.301. If you guys were in 3rd grade, and I asked you to multiply 476 times 0.301, could you do it? Like, this is something we teach our 3rd graders to do, right? So you can look up in a table and figure this out, and then you can do this calculation in like 3rd grade. And so essentially, you got the answer without using a calculator by looking at it on a little piece of paper and doing a multiplication. That's how powerful logarithms are. I was able to figure out what is 2 times itself 476 times by doing multiplication and looking up this number in a table. In fact, I bet you back in the day, people were so good at this that they memorized what these logs are. They memorized what these numbers are. You only have to memorize like 10 different numbers, and then you can do all of these crazy problems. Yeah, they're just like multiplication tables, and they're really important. In fact, we way back in the day, and I can't say way back in the day because maybe this was not even like, this was almost after your grandfather's generation and maybe before your father's generation. We used to put these logarithm tables on rulers. And we used to have the rulers that we would be able to move in and out and then be able to kind of look at this thing and say, oh, I figured out, like, here's the table. And those rulers are called slide rules. So engineers would have a little slide rule right here that, they carried around like their little gun. And they'd be like, whip out the slide rule, and move this thing around, and be able to calculate ridiculous numbers by just doing this. Because the only calculators they had were the 10-button calculators. Right? They didn't have these fancy calculators. So not even a generation ago, like the people who use that aren't dead yet. They're maybe my grandpa's age, or they're maybe my dad's age. So I'm assuming that might be your grandfather's age. Yeah. So anyway, that's the power of logarithms. They're actually really cool. They're really helpful and extremely useful. And in science, you use them a lot. And you have all these crazy properties, and I wish I had the time to explain all of them to you and that kind of stuff. But really, if you get really good at this conversion to be able to go from this thing to this thing right here, then you're good. Oh, by the way, I might have skipped some steps over here, or maybe you didn't understand every single step over here. Let me show it to you real quick. 143.29. 143.29 is the same as 143 plus 0.29. No arguments there, right? And then if I wrote this out as, if I have some number to an exponent and I have the same, and I'm multiplying by the same number, or by a number to the different exponent, I just add the exponent. So I kind of just used the reverse of that property, and I said, well, that's just 10 to the 0.29 times 10 to the 143. Because if you use this property of, look, same base, different exponent, you add the exponents, you can go from here to here. You see that? And then this number right here, this gives us how many zeros there are, and this number right here, this gives us that number, like what the actual number is. But what I'm saying is this number is actually the one that's more important. It's a math game that a physicist made up called, his name is Enrico Fermi. It's a fascinating game. Basically what happened is, he's the guy who kind of worked on the atom bomb. And when the atom bomb went off, he took a piece of papers and he dropped them on the ground, and then based off of the angle that the paper flew back at when the bomb went off, he was able to calculate the atomic bomb to be, I would say, about 375 kilotons of TNT explosive. And then they spent like 3 weeks doing the actual calculation, and then it came out to be like 376 kilotons of stuff. And so he was like, look, I got that after 3 minutes of thinking. I just thought about it. You know what I mean? And then so they have this whole slew of problems called Fermi problems. And they're actually quite a bit of fun. You would ask questions like, how many piano tuner, all right, here. Let me go into this tangent real quick, because I think it's relevant, okay? On an interview, I was once asked, they said, all right, Mr. Dalday, how many gallons, so they finished all my interviews, the questions like, what are your strengths, what are your weaknesses, what makes you laugh, what kind of, do you like long walks on the beach, that kind of stuff. And then one of the questions they asked me, and this is for a big time like engineering job, or not engineering, but like a research position, but they asked me, they go, how many barrels of crude oil is shipped into America every year? And I said, what? No, here's what I said. I looked them dead in the eye, and I said, okay, my answer is, there are 300 million people, give or take, in America right now. Of those 300 million, I would say that there is an average of maybe one car for every 3 people, if you're considering little kids and couples and all of that kind of stuff. 2 cars per family on average, and the average family is 2.5 people. So based off of that, I would say that 1 car per person, each person drives to work maybe about 20 miles. Factoring in the fact that you get about maybe 15 miles per gallon on a good day for cars. Some cars range to 20 miles per gallon, but America has a lot of SUVs, so we're looking at 13 miles per gallon on that side. So I would say that that's my number there. And so I'm writing all these numbers down on a piece of paper, like a napkin or something like that. I forgot. And then what I said was, based off of that, then what I would say is I could multiply that oh no, I say 20 miles to work every, there and back, and they do that every day, and they do it 5 times a day. So I multiply 5 times 52, and I get this number. And then what I'm going to do is I'm going to multiply 52 times, like what I do is I say, this is the gas mileage, so I can tell you exactly how many gallons of gas is being used in America every year. And then based off of how many gallons of gas is used every year, I can tell you exactly, well, I told him one of the things I don't know is how many gallons of oil does it take to create 1 gallon of gas, and then so I said I'm gonna assume, let's say 2 gallons of oil makes 1 gallon of gas. I don't know if that's the right answer, but I just I'm just telling him all of this stuff, and I say, and then let's say that there's about 50 gallons in each container of oil. So this is how many barrels of oil that is shipped into America every year. And I gave him some number, right? And he said, that's the closest anyone's ever got. So he shared with me the actual answer. He said, it's something, something, something. And the thing is, and I looked at him and I said, but here's the important part, is I got the right number of zeros. I didn't get the number right, but I got the right number of zeros. So I was offered the position. The reason being is because what he said, well, the reason why he asked me a dumb question like that on an interview question is mainly because he wanted to see, he wanted to hire people that wouldn't say something dumb like, I don't know, but I can get back to you on that, whatever. He wanted people who are persevered, who actually who just went in and tried something. You know what I mean? Yeah, I didn't even need to get close to an answer, to be honest with you. He just wanted someone who didn't say, I don't know. I give up. Don't hire me. That's too ridiculous of a question. So that's a good thing for approximating things like that. And then I remember on an interview, then again, I go to weird interviews because I apply for weird jobs because I'm a science guy. But I remember, I think it was on an interview or it was on a test or something like that, and it was just asked me to straight up calculate 2 to the 400th power or something like that. And like I was able to do it, and the hard part was they don't give you a calculator. But they said, how many zeros are in this thing right here? And I was like, well, this is your answer right here. So, anyway, I hope that helps. I hope that was a lot of good information. Sophia, I'm printing a catapult. Sophia, there's a few problems. Diamond, do you remember what do you remember what the thing was that we needed to, or no, which problem we solved on Monday or Wednesday? I'll tell you what, I'll just upload Wednesday's archive, and Sophia, you can go watch that one, because I solved the problem using logarithms from your exam. I think it was question 29. But I don't remember what that question was. Anyway, I gotta go. I'll talk to you later. It takes 14 hours. It's resting right now. Okay, goodbye.